Imagine you have 10 errands, 2 people to do them, and some tasks depend on others. How do you finish everything fastest? That's exactly what scheduling algorithms try to solve. In my last 2 videos, we talked about what a critical path is in scheduling, and we explored the list processing algorithm. We also discovered the order of your tasks, the priority list, can determine whether your finished schedule is actually optimal. But with so many ways to determine that priority list, how do we know what will give the best result? Since the critical path determines the fastest possible completion time for a set of tasks, it makes sense to work backwards from it. Let's look at an example, an order requirement diagram with 10 tasks of varying time and connections. We have 2 processors in this scenario. This can represent a lot of things, like you and your spouse running errands or 2 teams building a drone together. We're using the list processing algorithm, but first we need to create our priority list. Here's how it works. There are 4 paths from start to finish. 2 of them, T1, T2, T3, and T1, T4, T3, have the longest length, 64. According to critical path scheduling, we find the task at the head of the critical path and place it next on our priority list. Our list is empty at first, so T1 goes first. Then we remove T1 from the digraph and reevaluate the critical path. Now, the new critical path is T5, T6, T4, T3, with length 60. So T5 is placed second on the list. We repeat this process. Remove the head of the critical path, reevaluate, add the new head to the list, and continue until all tasks are listed. In the case of a tie, we simply pick the task with the lower number. Once the priority list is ready, we run the list processing algorithm. We choose a ready task that's highest on the priority list and assign it to the first available processor. For a slower, more in-depth explanation, check out my last video. Following this, we get a schedule with no downtime in between tasks. The total time to complete all tasks matches the critical path from the original digraph, meaning in this case, our schedule is optimal. So why doesn't everyone always use this method? Let's see what happens when we try it with a different example using 4 processors. The same algorithm produces this priority list, but after running the list processing algorithm, the schedule is actually the worst possible for this scenario. Here's what the truly optimal solution looks like instead. So what gives? Why the difference? Critical path scheduling is a heuristic algorithm. It usually gives good results, but it doesn't guarantee optimal schedules in every case. Its main purpose is to give you something solid to work from, especially when scheduling gets complicated. This connects to the famous P versus NP problem in computer science. Scheduling tasks optimally in general when you have complex dependencies and multiple processors is an NP hard problem. That means there's no known algorithm that can always solve it efficiently in polynomial time. There are too many moving parts that make the time required to find the optimal solution increase exponentially as the situation grows. I talk more about this in my heuristic algorithms for the traveling salesman problem video. It's a super interesting topic, so check out that video if you're interested. Thanks for watching, and stick around for even more cool math stuff.